The idea of restoring the functionality of a limb lost by an amputation with a robotic prosthesis or a bionic limb has been around for a very long time. However, you will be amazed on how little prosthetic devices given to patients today have changed in the last decade. And this is because of a variety of problems, and I'm going to tell you how in my group we're tackling two of the big ones. That is, how you attach the prosthetic device to the body, and how can the patient control such artificial replacement. So let's talk about the first one. Have you ever had a blister on your feet because of bad fitting shoes? And why did that happen? You have compression of soft tissue and friction, constant friction because of movement. Sockets, the conventional technology to attach a prosthesis to the body, works on the principle of compressing the stump in order to create enough suspension to keep the prosthesis in place. And as you can imagine, this is uncomfortable and it can be painful. But it works for some patients, and they learn to tolerate it. For some others, however, this is not good enough, and they will choose not to wear a prosthesis at all. If you have a short stump, there is not enough space for the socket to grab in, so you end up blocking or limiting the range of motion of other joints. In this case, this patient has a socket and suspension components, and he cannot raise his arm higher than that. So the cost of wearing a prosthesis comes to sacrifice mobility in other joints that otherwise are fully functional. A solution for this problem was actually found in Sweden and in Gothenburg with the discovery of osseointegration. And osseointegration basically means that if you put a titanium implant in bone, bone cells will grow tightly around it. And this integration is so strong that you can actually attach the artificial limb directly to the skeleton. I have the privilege to work with Dr. Richard Bronnemark, who is the pioneer of this technology. He and our colleagues in Gothenburg have spent decades of research developing a treatment that has now been used to treat different amputation levels, and is considerably improving the quality of life of hundreds of patients around the world. So osseointegration seems to be a technology that's taking care of the first problem. Now let's talk about the second one. How can the patient control the prosthetic device? There was a time when the prosthesis itself was the bottleneck. However, with the development of electronics, motors, batteries, and materials, engineers can now develop very sophisticated hands and arms that not only look really cool, but have all the potential to restore the missing functionality. If only patients could control that many degrees of freedom or robotic joints. There are different approaches to solve this problem. One of them is using electrodes on the surface of the skin, as you can see around my forearm. And then these electrodes will pick up the electrical activity of the muscles, and then we can use algorithms to decode the bioelectric signature of each movement. So if I lose my hand around this height, I can still control every finger of the robotic hand in a similar way as I will do with my biological hand. And we can use other machine learning techniques and control simultaneously different joints of the prosthetic device. And if you think about it, now that we have this technology to predict the intention of movement, we can control a prosthetic device or games entirely with hand motions. And this looks like fun. Well, it's actually a lot of fun. And that's why we're using it as a tool for neuromuscular rehabilitation and treatment of phantom limb pain. A tool we decided to do open source, so other people could go and try it and improve it and do something with it. So you might think, problem solved. We can predict movement, we can control the prosthetic device. The problem is that this technology works very well in the lab, but it's hard to get it stable out of it. The thing with prosthetic devices is that these are not toys, because a toy you can choose when to play with it. Patients need their prosthesis in the morning when they wake up, to get dressed, to cook, to eat, to go and work and earn a living. And if the prosthesis is malfunctioning, is not doing what it's supposed to do, they will eventually throw it away. It's not uncommon to meet patients that although they have the resources to afford the most expensive prosthesis, they will choose not to use anything at all because the functionality is so poor that at the end of the day, they're better off without it. So functionality, reliability, easy to use is very important in prosthetic devices. And getting signals from the surface of the screen compromises reliability. Conventional technology uses a socket for suspension, surface electrodes for control. With osseointegration, we move from suspension to fixation, which is a lot better mechanical coupling. We get rid of the problems related to the socket, And although this alone has a lot of advantages, we're still limited on control by the surface electrodes. So what we decided to do in my group is take this technology further and develop it to be a communication port between implanted electrodes and the prosthetic device. If you go inside the body, you have access to more muscles, you have more reliable signals, and you have access to nerves. Nerves carry the control information from every muscle in your limbs, but also information from the sensors in your hand back to your brain. And very importantly, those neural pathways are still there after an amputation. This is Magnus. He's the first patient we treated with this technology. We developed electronics to make the system self-contained, so he simply needs to take the arm, push it in, close the clamp, get mechanical connection, and at the same time, electrical connection with implanted electrodes. So he can control the arm in any position, which was previously not possible with surface electrodes. This technology has allowed us to truly integrate biology and mechatronics. This is the first time that the man and the machine have such an intimate connection at many different levels. The artificial arm is directly connected to the skeleton, and the human control system, that is nerves and muscle, also have a connection with the artificial device. How cool is that? Thank you. But, this sounds great, but what does it mean for the patient? Well, now because the electrode is directly on the muscle, he needs to contract it just a little bit, and that signal will be enough to drive the prosthetic device. And that basically means that he has a more precise control of the hand with very little effort, as opposed to surface electrodes where the signal will need to travel between soft tissue, fat, skin, dead skin before it can reach the electrode on the top of the skin. Another problem with recording from the surface of the skin is the skin moves a lot. It's a polarized, high-impedance interface where electrical artifacts can easily happen because of movement. And this basically means that if the patient moves too fast, the hand will actuate without him wanting to. So if he's holding an object, in this case an egg, and he moves too fast, the hand will either crush it or let it go. And this, of course, limits the kind of things you can do with your prosthetic device. This doesn't happen with our system. It's very reliable to motion artifacts and electric interference. So the hand will not open or close without him wanting to do so. Like now when he's crushing the egg to show that it wasn't a fake one. So he can use his hand in any position to do all sorts of different stuff. And that's something quite amazing from someone with an amputation level like him. And all these are cool demos, but they translate in things that the patient can use his prosthesis for. A big problem for Magnus was not being able to use his prosthesis in cold environments. And that can be a problem living in Sweden. So during the winter, the skin will get dry, and the signals will not translate very well to the surface electrodes. So he could not use the prosthesis. But now, since there is no skin interface, he can use his prosthesis at minus 30 degrees in skin up north in Sweden, or when he's in holidays at plus 30 in the beach, without touching whatsoever the prosthesis. So the prosthesis will just work in any environment, in any condition. All this makes the prosthesis fundamentally more reliable. And if it's more reliable, it's more useful. And since there is no surface components pushing against your skin, it's also more comfortable. He will sometimes sleep with the prosthesis. We don't know any other patient that does that, because if you have the skin components pushing on your body, it will be like sleeping with your shoes on. So this tells us a little bit about the integration between man and machine and how this happened and at which level. This is the first patient in modern times that has been implanted with electrodes permanently, and that's actually using them to control a prosthetic device in activities of the daily living and at work. He went from working 50% to 100% because the prosthesis is not a limitation anymore. This system has been stable for almost 2 years now. Demonstrating the long-term stability of this system was very important for us because it is that what makes it clinically useful. And with that I mean that we can treat patients and they can take this technology home and not only in the lab. And that's probably the major contribution of our work to the field. This interface is bidirectional by nature. And this means that we can stimulate the nerves in order to create the perception of sensations coming from the missing hand. Pretty cool as well, huh? Magnus lost his arm over 10 years ago. And we found that with a single electrical pulse delivered to the nerve that used to be connected to his hand, he will feel like you are touching him. And this is very important. It's been stable for several months. And the reason why this is important is because today, no prosthesis given to any patient used in the real world provide any tactile or proprioceptive feedback. But with our osseointegrated interface, we can make this happen outside of the lab where it matters for patients. So all this is very exciting, but the most exciting part is not what we have achieved so far, but all the new possibilities we can make with this technology. The aim of our group is to provide a very good mechanical coupling that allow free range of motion for the joints that the patients still have. And now that we have a permanent connection with the neuromuscular system, we can use that to get signals of control from the brain. They come down in the nerves and the muscles. We can combine them with surgical techniques. We can use our decoding algorithms to tell the prosthesis what to do. Put sensors in the hand so the hand knows when it's touching something, what is the position of the hand, how much force is put in an object, and translate that via neurostimulation so the patient will feel as as he's touching with his real hand. It's a very intuitive control. You probably can see there's a lot of different fields involved in this project. We have a technical institution, we have a medical institution, an industrial partner. And if you take any of them out of the equation, this will not happen. The engineers cannot do it alone, the doctors cannot do it alone, an academy by itself will not reach a clinical implementation. So we're very fortunate to have this framework of research where we can make things like this happen. So far, we've been focusing on the upper limb, but our technology equally applies for the lower limbs, so we can treat patients that we have implanted in the lower limbs as well. And we're looking to provide neural control for prosthetic devices at different amputation levels. This is my and my group vision on the future of bionic limbs. Thank you.